Today's target will be simplifying radicals. By the end of today's lesson, you'll be able to simplify a square root of an integer, simplify a square root of a monomial expression. It's just a number with variables attached. And lastly, simplify a cubed root of a whole number. I know you've seen square roots in your pre-algebra classes. I do not think you've seen a cubed root, so that'll be something new to you, but it's very similar to a square root, so it shouldn't be too overly complicated. As always, if you have questions as we go through this video, please make a note of it so we can discuss your questions in class. A couple prerequisite knowledge skills that you need to have. First is the concept of a prime number. A prime number is a number that is only divisible by 1 and itself. Your examples would be 2, 3, 5, 7, 11, 13, 17, and 19. You can continue on. Our purposes, we're going to use, for the most part, prime numbers 2 through 11. We're not going to see too many examples where we need to get any bigger than that. So 2, 3, 5, 7, and 11 are the main prime numbers that you'll be looking for, and I'll explain more on that here in a minute. Second prerequisite knowledge skill that you are going to want to have is the concept of perfect squares. Perfect squares are numbers that when you take the square root, they result in an integer. So your perfect squares would be 1, 4, 9, 16, 25, and 36. So that means if I take the square root of 16, it simplifies to 4. So that's why 16 is a perfect square. These are not necessary knowledge skills, but if you have them, it will make your life a little bit more easy. Example number 1. So follow through as we go. Our primary objective is to find the factors, more specifically the prime factors of the number under the square root, in this case 75. So we're going to break 75 down. We could break it down as 25 times 3. We're going to circle the prime factors. So 3 is prime. We're going to circle that. We're done with that side of the tree. 25 is 5 times 5. Both of those are primes. So once you get to a point where you have all prime numbers left over, you have completed step number 1. So we can rewrite the square root of 75 as the square root of 5 times 5 times 3. Good habit to get into, to go ahead and check your work, multiply those numbers back together, and make sure you get back to the number you started with. So you can use a calculator. 5 times 5 times 3 would give you 75. Step number 2, we're looking for groups of 2 similar numbers. So we're going to look at what we have. We've got 2 5s. So that's my group. From that group, I can pull 1 outside. That's what a square root does. It takes a group of 2 and it makes it a group of 1. So the group of 5s can come outside. The 3 does not have a pair, so it has to stay inside the square root. So I now have 5 outside the square root, 3 inside the square root. And that's as simple as it's going to get. Here's example number 2. Now we've got some variables. We're going to start with the number, break it down just like we did the previous example. So 54 is 9 times 6. Neither of those are prime numbers, so we're going to break it down again. 9 is 3 times 3. Both of those are prime, so we're going to go ahead and circle them. 6 is 3 times 2, so we're going to go ahead and circle those guys as well. So now we've got the square root of 3 times 3 times 3 times 2, x to the 5th, y to the 4th. We're looking for groups of 2. I've got a pair of 3s. I can pull that outside. Since these guys are 2 different numbers, I cannot pair them up. So they have to stay inside. So I've got 3 I'm going to go ahead and multiply them back together to get 6. Okay. And then I've got x to the 5th, y to the 4th. Well, I want to break these down too. So x to the 5th means I have 5 x's being multiplied together. Y to the 4th means I have 4 y's being multiplied together. So I want to look and say I can make 2 pairs of x's with 1 left over. And I can make 2 pairs of y's with none left over. So from each of those pairings, I can pull that many x's out. So I can pull 2 x's out, so I have 3x squared. And I can pull 2 y's out, so I also have y squared. Underneath the radical, I still have that 6, and I also have the x that's left over without a pairing. This is our complete answer. Make sure in a problem like this that you not only simplify the number, but you also simplify the variable. A lot of students will simplify the numbers correctly, but they'll leave the variables by itself, and that's not a complete and correct answer. All right, our last example is that with a cubed root. That 3 there is indicating to you that this is a cubed root and not a square root. The only change in our process here is that we are now looking for groups of 3. So that means we're going to still start by breaking it down. So 200 could be 20 times 10. You could also do 100 times 2. You break down however you want, but the point is that you keep breaking it down until you get prime numbers. So 10 is 5 times 2, 20 is 4 times 5. Every time I find a prime number, I'm going to circle it. So 200 breaks down as 2 times 2 times 2 times 5 times 5. So 3 2's and 2 5's. So when I go to rewrite this, I've got the square root of 2 times 2 times 2 times 5 times 5. And remember that now we're looking for groups of 3. We've got 3 2's. So I can, out of that group of 3, I can pull a 2 out. I've only got 2 5's. So while if this was a square root, I would have been able to pair those 5's out, pair those 5's up, and take 1 out. However, it's now a cubed root, so I can no longer do that. So those 5's are going to stay underneath the cubed root, and my answer becomes 2 cubed roots of 5 times 5, which gives me 25. So 2 cubed roots of 25. And that's my final answer. Now it's your turn. You've got 2 examples here. Pause the video now and give them a try. The answer to our first example would be 2x to the 3rd y times the square root of 5y. You can see 20 breaks down as 2 times 2 times 5. So we can pull out a pair of 2's. And we have 6 x's, so we can make 3 pairs with none left over. And we have 3 y's, so we can make 1 pair with 1 left over. So the 5 and the single y get left by themselves and have to stay underneath the square root. Everything else that has a pair gets to come outside the square root. In our second example, we have the cubed root of 135. That little 3 on top of the root tells us that we need to look for groups of 3. So 135 breaks down as 3 times 3 times 3 times 5. We've got a group of 3 3's, so we can pull a 3 outside. However, the 5 does not have a group, so it has to stay underneath the radical. So our final answer would be 3 cubed root 5.